So today we're going to organize all of this crazy mess with term symbols. And so that's the focus of today. So we're going to go back to that Atomic Spectral Database and look at the output that we saw at the very end of last lecture. And we're going to zoom in on those term symbols. So this is the Atomic Spectral Database. We talked about putting in your element, the range if you're doing spectroscopy to get the spectral lines. You could look at the Grotrian diagram and so on. And so here's the Grotrian diagram that the Atomic Spectral Database produces for mercury. We went through all the electron configuration. That's what the little fire dog was confused by because it was just everywhere. And look, this is fine. Okay, this is the spectrum that's coming out of these mercury fluorescent lights that was actually taken here at the building. This isn't from the internet. Okay. And this is the specific wavelengths of all of those lines in the spectrum. Now we only see a few in the spectrum, so we can see that the 435. That's this one right here. Okay, so that's an intensity of 4,000 relative intensity. Then we have the 546, which is right here, right below 550. And then we have this 576 at 240. And so that's this one right here. So those are tiny little lines. What about this big red one? Well, if you look up here in the spectrum, I know it's too hard to see, but it says Roman numeral 2. So that's the mercury cation. So the red line comes from the cation. So that's why the mercury lights appear to be green when they start up and they're not hot yet. So then it gets hot enough to generate enough ions that once the ions are there, then they can get the red photon. But what are these terms? We look up here, we see the electron configurations, left and right, and some of these are identical. So we have 5d10, 6s, 6p, and it's going, that's the lower state, this is the upper state, 5d10, 6s, 6d. Okay, that's a different one. There's one that's the same. There may be, but I don't see one up here. But they have these terms that are associated with these electron configurations. And so this is what we're going to focus on today. And so for helium and everything more complicated than helium, we have multiple electrons. We could have these paired and unpaired electrons. We could have triplet and singlet states and so on. And we can organize the Grotrian diagram based upon the spin states of the electrons and what orbitals those unpaired electrons are in. So that's where we get these things called term symbols. They're all over the Grotrian diagrams. And it's a way for determining the difference between these identical electron configurations. So what is the difference between a 1s, 2s, and a 1s, 2s? Okay, this one over here has got paired electrons because it's a singlet state, and this one has unpaired electrons. And it's very easy to understand for helium because we only have 2 electrons. So we have, say, a spin up in the s orbital, and if that spin down electron goes to the 2s orbital, then they're still spin paired even though they're in different orbitals. Okay. And so that's the singlet. That's that little superscript that you have. And if that one unpairs, it drops in energy. You see the drop in energy. And now it's still a 1s, 2s, but the spins are unpaired. And so it's a triplet state. It's the number of unpaired electrons plus 1. That's all you're doing for the multiplicity. And so these are the initial considerations for building up these term symbols, okay? We're only talking about electrons in unfilled shells. Okay, and the term symbols for ground state atoms with completely filled subshells are singlet S0. So all of them are singlet S0 that have a completely filled subshell. So those are all of the last ones in each group. You see beryllium group all the way down. You see the zinc group, zinc, cadmium, mercury, and then all the way over to the noble gases, helium, and all the way down. All of those have the same term symbol of singlet S0. They're singlet because all the electrons are paired up, and they're S because it's there's no net angular momentum because there are no unpaired electrons. So when we're trying to come up with this capital SPDF, we're trying to get a feel for the angular momentum total in the electron cloud, not just for one electron. So this is the whole electron cloud. All of the angular momentums, like the M sub L's, one is a plus one is a minus one. Well, they cancel out if they're both filled up. And so when you filled up all of those angular momentums and their magnetic components, then you're back to an S term of zero angular momentum. So here's this scheme called the Clebsch-Gordon Series. And it's just, there's no better way than to use this series to come up with all of the term symbols. And so let's look at the vocabulary first. The capital L is the total angular momentum. So it is case sensitive. The little L's are the L quantum number for the unpaired electrons. So each individual electron has a little or lowercase l. But then capital L is for the whole atom in the whole electron cloud. The atom is the electron cloud. That's the capital L. Okay, so capital L is made up of these little L's, and we come up with this whole series. So this goes far back. Do y'all remember ever covering series where you have the little bracket? Yeah, so I don't remember when y'all cover that in your K through 12. Do you remember? Was it recently or was that like in middle school? Don't remember? Yeah. Yeah, okay, but not recently. We'll just assume it's not recently. So it's just a series of numbers. That's all it is. Now, all of ours are going to be integers. They can be negative, they can be positive. No. Let me think. The M sub L is a series that can be negative, but these L's are all positive. These are all positive. Okay. So the little L's add up, and you have a maximum value and a minimum value. You also have this number of multiplicity. So the multiplicities are these superscripts. I would say superscript prefixes. Okay, these are the multiplicities. And those are made up of the individual spins of the electron. So plus 1/2, minus 1/2, and so on. And then the total angular momentum quantum number is the L plus S. So we take the multiplicity and the angular momentum quantum number, and we make a new series out of that. So those go down here, and we come up with the J values. Now this J value is the total angular momentum quantum number, not the rotational quantum number. Can everybody read that? Not the molecular rotation quantum number. So it's just, there's so many things in science, we run out of letters. Okay, so J in terms of atomic, electron cloud, term symbols, is the total angular momentum quantum number. And so it shows up down here as a suffix, subscript. Okay, so J goes here, the multiplicity goes here, and then the capital L's go here in the middle. Now we have a series, so whenever you have a series, you're going to have different L's. And so for each one of those L's, you have a different term. So you may have a whole bunch of terms for a particular type of atom. Because look back here, let's go back a little bit and see. Here it is for mercury. So look, this is all mercury, right? But look at all the different terms mercury can have, because it can have different excited states. And so if we put an electron in the d orbital, there's lots of results of that. You can have it in the d orbital spin up, you can have it in the d orbital spin down, you can have it in the d orbital in the m sub L plus 2, or the m sub L plus 1, or the m sub L 0, the m sub L minus 1, the m sub L minus 2. And then you can have all those options with this electron pointed down. So think of all of the different options you have for all of the quantum numbers. It's really confusing. And that's what this Clebsch-Gordon series is meant to keep track of. So it keeps track of all of the different ways the electron cloud can be built. And they all have energetic effects. So let's practice. We've got to learn by doing, right? So let's just start with a very simple atom with just one electron, one valence electron, one unpaired electron. Let's do sodium, okay? So here's sodium, the ground state electron configuration. And that's a nice thing. We can start with the ground state electron configuration, and it can also apply to all of the excited states with that same electron configuration. So this is pretty simple. The L series only has one little l. We only have one electron here, and this electron this valence electron is in an s orbital, so L equals 0 for that electron. So capital L should be L1 plus L2, but there's no L2. Why not? Well, sodium has 11 electrons. So where are the other 10? Well, they're captured in that core, the neon core, and they're not participating. So we're only interested in the unpaired electrons. Okay, so we have just one unpaired electron, so we only have one little L. And so we only have one term. The term is S. Okay? And so we use the same rules for the capital L that we do for the little l's. And so if it's a capital L of 0, that's an s orbital. If capital L is 1, that's a p orbital. If capital L is 2, that's a d orbital. Or a d term, I should say. Okay. Now let's do the multiplicity. So the little spin for this, we will assume that they're spin up first. So we'll do spin ups first and then spin downs if we want to pair them up. But we don't really have to worry about that because the Clebsch-Gordon series captures where they're added together or when they're opposite of each other. We only have one electron, okay? So it's a plus 1/2 spin. So the multiplicity is 2 times 1/2 plus 1, or 2. It's a doublet. Number of unpaired electrons plus 1. So that's pretty easy to calculate. So why are we multiplying it by 2? Well, the spin is 1/2. So when you multiply it by 2, you're counting however many halves you have. So that's how we get the number of unpaired electrons. We're taking the spin 1/2, multiplying by 2, so we get a count of the unpaired electrons, and then we add 1 to that, and that's what gives us the multiplicity. So if we have one unpaired electron, we have a doublet. So we could write the term right now. We could say this is going to be a doublet S. But we don't know what goes down here in the bottom. But that's the term. We have to figure out what J is down here. And so to get that subscript, let's go ahead and do the L plus S down to L minus S. So we have a max value, and we have a minimum value. And then we go in between by integer units. We really won't see anything interesting in terms of sodium because there's just one electron, but when we get to carbon, it'll be much more interesting. So we have 0, which is L, 0 plus 1/2, and then it goes down to 0 minus 1/2, which you might imagine would be negative 1/2, but this has absolute 0, so this is important. There's no negatives, okay? So we take the absolute 0 of that, or the absolute value of that, and we end up with plus 1/2 here, and we end up with plus 1/2 here. And there's nothing in between those, right? And so our only term that survives is plus 1/2. So we only have one J value for this system. So we're only one term, the doublet S 1/2. And notice we didn't use the principal quantum number in any of this. So N wasn't used in any of this. So this applies to any NS1 configuration. So this would also apply to the excited state sodium atom where it's in the 4s orbital, or the 5s, or the 6s. And so this whole column could be labeled with the doublet S 1/2. Now I added the little Grotrian diagram in the notes yesterday, so it's not in your handout. But that's just showing you that this is a way to organize and label those columns in our Grotrian diagrams. Okay, what about this column over here? What if we move that electron over here to what's the next available p orbital, or the first available p orbital for sodium? First of all, what's the sodium valence electron? It's at 3s1. So what's the first available p orbital? Crickets. What's that? Yeah, so if we look at it, sodium is past the second row, it's on the third row. So since it's past the second row, the two p orbitals are all full. Every one of them has electrons in it. So the next or first available p orbital is the 3p. So this one's 3p. This is the 3s. So this is the 3s1, 3p1. So see down here, this 2p6ns, and this is the 2p6np. So 3p, this then is 4p, 5p, 5p, no, 55. This is the 3s, this is the 4s, 5s, 6s. All of those have the neon core and then 6s, etc. Okay, so let's look at the term for this 3p1. So we have an excited state sodium atom. So L equals 1 because this little l here, little l equals 1. And we can't say L1 plus L2 because we don't have two unpaired electrons. So our series in this Clebsch-Gordon series, our series for L is really small. It's just one term. So the term is P. And that's because that sole electron is in a p orbital. Then the S is the same kind of thing, one unpaired electron, so we have a doublet. But now it gets a little more interesting with the J values. Okay, so the L plus S, we have J plus a half, S is 1/2 because we have one unpaired electron, all the way down to L minus a half. Okay. And so and this is a funny way of writing it. Instead of writing this as 1.5, they just call it 3/2. And this is 1 minus a half, and so it's 1/2. So we have 3/2 and 1/2. And are there any units in between? Well, you can take the 3 and subtract 2 until you get to the farther right one, and 3 minus 2 is 1, and so you're already to the minimum value. So this is the maximum value, max 3/2. This middle piece right here is 3/2 minus 2/2. That's the same as subtracting 1. And then this minimum value equals 1/2. Well, this piece right here, if I calculated it, that's 1/2. And so we can't have duplicate terms, so I'm already at the minimum. So if we subtract 1 from the max value and we're already at the minimum, we're done. We say that again. We start the max, we calculate the max and the min, and then we go to the maximum value, subtract 1 from it. And if we're already at the minimum, we're finished. We're not always going to be at the minimum, but let's say we subtract 1 and we are at the minimum, then we only have 2 terms. So these are the term symbols for the excited state for sodium with an electron in the p orbital. Now, once again, we didn't use N in the Clebsch-Gordon series, so this applies to every situation of an NP1. And so that doublet P can label that whole column. Okay, but what about the 3/2 and the 1/2? Where do we see that in the column? Well, we have to zoom in. If we zoom in on that level, we would see a splitting. So we would see this, what they call hyperfine splitting, meaning really, really fine splitting in those energy levels. They're not quite degenerate. There's just, we'll see in the next slide that the energy difference. But look at that. It's about 15, well, what would you estimate? 17,000 wave numbers? This is 0. Look where that level is. 17,000 wave numbers. That's the energy of that level. What do you think the splitting is? The splitting is about 17 wave numbers. So it's hyperfine splitting. It's a split between the J values of only 17 wave numbers on top of 17,000 wave number energy for that level. Okay, but we can see that in the spectrum. And so you can see the difference between those, the P, doublet P 1/2 and doublet P 3/2 energy levels is 17 wave numbers, and it's roughly way up at around, close to 17,000 wave numbers. And so the emission lines for sodium, these are the two emission lines. They're called diffuse lines. That's what the D stands for. It's not a term, it's just a description of the lines. And notice that the only difference is they're both at 589 nanometers, but they're about half a nanometer, or about 0.6 nanometers apart. And we can see that pretty easily with the spectrometer. So if we can do this once with sodium, NP, and get all of the energy levels in that column, they have the same term, then we could do this for all of the possible configurations. And so if we just have an S1, like the sodium ground state configuration, all S1s are going to be doublet S. So all of the S1 electron configurations are going to have this term for their ground state. So that means cesium, rubidium, everything. So the H group. And also all of the, I guess, +1 cations. I know that group 2 wants to be +2, so it can have a noble gas configuration. But let's say we had a calcium 1+, then it would be an S1 configuration. So this would be the terms for that. Okay. What about P1s and P5s? Well, P1s would be boron, aluminum, gallium, boron group. And P5s would be the halogen group, boron group and halogens. Now, why is a P5 and a P1 the same term? Well, think about this. We're only concerned with the unpaired electrons. And so a P5, let me just write this up here. P5 equals your 3p orbitals, and you have spin up, spin up, spin up. So if we're filling them like the Aufbau scheme says, we put unpaired electrons in all 3 orbitals first, and then we've got 5 of them to put in, so then we start pairing them up, spin down, spin down. A P5 has 1 unpaired electron in a p orbital. And just like a P1 would have 1 unpaired electron in a p orbital. So P1 and P5 have the same angular momentum of their electron cloud. They have 1 unpaired electron in a p orbital. And then P2, those would be the carbon group. You can see that P2 over there. It's the second column in the P group. So carbon group. And then what's the other one? The P4s. That'd be the oxygen group. And then the P3 would be the nitrogen group. Then we get into the Ds. And so you could do the same thing. The D1s would be scandium and D9 copper. So copper and scandium would be the same terms. The D2s and D8s, so titanium and nickel and so on. So you could work your way through and show all of these. Now notice the ones with the most unpaired electrons and the highest angular momentum would be like the D5. So this has the most terms. Why is that? Well, because you've got all of the possible ways to put together 5 electrons in a d orbital. One, two, three, four, 5. Okay, so that's the ground state or lowest, by Hund's rule, that should be the lowest energy electron configuration. But you could also do 1, 2, 3, 4, 5, right? You could pair one up and leave one blank. And you could do all of these different things and get all of these terms. So the more flexibility you have by having more unpaired electrons, the more terms you end up with. And so the D5 on this list is probably the most complicated, although it looks like D4 and D6 are just as complicated. We're not going to do anything with more than 2 electrons, okay? So it's just the same skill, but it's just more tedious. So it's nested. So I don't know if you ever played the game with the towers, the cups. There's a procedure for moving all the cups from one spot to another, and it's the same procedure, and adding more cups only just takes it's probably like the square of the number of cups in terms of how much time it takes. So the same kind of thing with this. Once you've learned how to do it with 2 electrons, doing it with 3 is the same set of skills, it's just longer. And have fun if that's something you want to try. Make a video, time yourself, yeah. Okay, so this small table gives the permutations within that ground state configuration for most of the elements on the periodic table. And it does apply, this way of coupling things really goes up to around the middle of the table, around zirconium and so on. Once you get below in the middle of the 5th row and below, then there's a different coupling scheme. So we'll just learn the one that deals with most of the elements we typically come across. The Clebsch-Gordon series that we're learning gives these plus all of the excited state terms. So let's do carbon. Okay. Now we know carbon has 4 valence electrons, so we might be worried, like, oh, it's got 4 electrons, but 2 of those are paired already, right? So carbon is past the 2s, so it's 2s2. So we're not interested in those 2 electrons. They're paired up. They're in a 2s orbital, happy. We're going to treat that as a core. So it's the valence electrons still, but we're going to deal with those unpaired electrons that are in the p orbital. Okay. And so those are the only 2 that we're interested in. So let's do the capital L's. So we go along, we have, again, 2 electrons in the p orbital. They're both p. So this p orbital means we have an L of 1. And the second electron is also an L of 1. So the max value is when both of those angular momentum quantum numbers are pointing in the same direction, and the minimum value is when they're pointing in opposite directions. And so that's why we go from the max where it's plus and to the min where it's the difference between the 2. And so we have a max value of 2 and a minimum value of 0. And those are p orbitals. Okay. So our L, we have the max, 2. We have the minimum, 0. Then we go to the max and we subtract 1 from the max and we get 1. We're not at the minimum yet. So we subtract 1 again and then we find we're at the minimum. So our full set is the max to the min with increments of 1 in between. Okay. So if our max was 5 and our minimum was 0, then it would be 5, 4, 3, 2, 1. We'd have all of those terms together. So then we go with these capital L's and we put letters associated with all of these, right? So an S is the 0, a P is the 1, a D is the 2, and we're using the capital letters for the capital L. So these are the 3 terms that we're going to have for this electron cloud on carbon. Now let's get the multiplicities for these. Okay, so our little s's are the spins of these electrons. And so we can go from plus 1/2 added to plus 1/2 all the way down to plus 1/2 minus 1/2. So the maximum value is equal to 1 and the minimum value is equal to 0. And 1 minus 0 is 0, so we're already at the minimum, so we only have 2 terms. We have 1 and 0. Okay, so that's the capital S. Okay, and then we figure out what the multiplicity is. So the multiplicity is this 2s plus 1. So 2s plus 1 equals the multiplicity. So when s equals 1, 2s plus 1 equals 3, and so that's a triplet. When s equals 0, 2s plus 1 is 1, that's a singlet. So we're going to end up with triplet and singlet. So we put the multiplicity up as the as the prefix superscript for these. So every one of these terms right here has every one of those S's. So our 3 terms now become 6 terms because we have 2 multiplicities times 3 terms. So we end up with 6 total types of term symbols for the P2 system. You have triplet D, triplet P, singlet P, etc. Any questions on this page before we get to the J? I'm going really slow because I'm trying to like just walk you through it, but that sometimes makes it sound like it's way more complicated than it is. It's not complicated, but I'm just going slow. Not because I have like it's so complicated I got to really walk you through it, but it's new, and so I want to make sure that you're following me each step. Okay, let's do J. So it's a nested problem. So for every one of these terms, we have an S and an L. So this is S and this is L, right? And so now we're going to make a series where we add S and L and we go down and subtract S from L. And so we got to pick a term and then do that. And then pick a different term and do it again. So every one of these 6 pieces has a J value for it. So it's a nested problem. So we come up with 6 terms, and now we have 6 little problems to do. That's what we mean by nested. So let's go through it. So for the triplet D, so we pick one of those terms, doesn't matter which one's first, but pick the triplet D. L is equal to 2. That's because it's a D. And here's where I think people will make the mistake. The S is not 3. This is the multiplicity. For a multiplicity of 3, S is equal to 1. Because the multiplicity is 2S plus 1. So if it's 3, then subtract 1 and divide by 2 and you get to 1. Okay. So we need to know S and L because for J, it starts out with L plus S, and goes down to L minus S, absolute value. And here's the absolute value is going to become important on some of these. Okay. Not on this one, but on some of them. Okay, so our L plus S is 3. Our L minus S is 1. So 2 minus 1 is 1, absolute value. So we go from 3 down to 1. 3 is the maximum value. 3 minus 1 is 2. 2 minus 1 is 1. We've got the whole series of 3, 2, 1. So those are our J values. So we're going to summarize later, but we could write it out now. We have a triplet D3, a triplet D2, and a triplet D1. So we have these little microstates in the hyperfine splitting. We have 3 energy levels that'll be labeled triplet D3, 2, and 1 in our energy level diagram. Okay, for the singlet D, L plus S, so we have L plus S. It's a singlet, so S is equal to 0, down to L minus S. Since it's 0, it's L plus or minus S is going to be no change. So we only have one J value for the singlet D, and so that would be a singlet D2. Then we pick the next term. That's the triplet P. So L equals 1 because that's a P. S equals 1 because it's a triplet. And so the J is L plus 1 down to L minus 1. So L plus 1 is 2. So L plus S is equal to 2. L minus S is equal to 0. And so we have 2 as a maximum value. We have 0 as a minimum value. We can fit 1 unit in between. So it's 2, 1, 0. So we have triplet P2, triplet P1, and triplet P0. For the singlet P, so L equals 1 because it's a P, and S equals 0 because of a singlet. And so 1 plus or minus 0 is 1. So we just have singlet P1. For triplet S, L equals 0 and S is 1. So this is where we need that absolute value. So here's L, because it's an S term, L equals 0. And then it's a triplet, so S equals 1. And so this one looks like it results in -1, but we take the absolute value. So since it's the absolute value at +1, so our maximum value is +1, our minimum value is +1, and so we just have one term, one J value for this term, and it's +1. Okay, and then for the singlet S, everything is 0. L is 0, S is 0, so we only have one term, which is 0. So these are all of the individual terms of those tiny little energy levels, the hyperfine levels for carbon. So this is quite a long problem. And on a test, it would take you a long time, and there's lots of places to go wrong. But you should be able to look at any one of these. And if I give you this one and ask for the multiplicity, what is the multiplicity of this term? You can look at it right there on the term. The multiplicity is the superscript prefix. So 3 is the multiplicity. But you could imagine on a multiple choice, right? 5, 4, 3, 2, 1. These are your choices, right? What's the multiplicity? You like, 3. Okay, write it down. There's 2 points. Go to the next question, right? What is the spin? This one, I guess the total spin for this state, okay? Since we have 2 electrons, so the multiplicity, let me find it here. So S, gosh, it is, I agree, it is somewhat confusing. When we're talking about this S right here, that's the spin, total spin. So let's pick this triplet P right here. So this is the total spin. So we have 2 electrons that are unpaired in this situation. So it's a triplet because we have 2 unpaired electrons. 2 unpaired electrons plus 1 is 3. So that's where the triplet comes from. So if I'm asking for the total spin for a triplet state, I subtract that 1 and I add them up. 1/2 plus 1/2 is 1. So the total spin for this state is 1. What about the J value? You could read it right off the term. This is J. What is the total? Let's go back to the vocabulary. What is the total angular momentum on this one? Let's go back, way back to the vocabulary page. Yeah. This is the. So we were just talking about capital S being the total spin quantum number. The L is the total orbital angular momentum quantum number. And it's just focused on the orbital. Because down here is the total angular momentum quantum number. So I agree, it's very confusing in terms of the vocabulary. So I put a big old star on this page for you in your notes. These are the terms that I'm going to be using in my questions. And so if I ask for the total orbital angular momentum of a triplet S1, the total orbital angular momentum of this S right here is equal to 0. Capital L equals 0. If it's a triplet state, capital S equals 1. if it's a triplet S1, J equals 1. And so those are the letters. If I ask for the total orbital angular momentum, it's 0. If I ask for the total angular momentum, it's 1. If I ask for the total spin, it's 1. If I ask for the multiplicity, this right here, it's 3. So there's 4 sort of groups of vocabulary, 4 vocabulary sets of terms. It's not a single word. Total orbital angular momentum is 4 words, but that's what capital L is. The total angular momentum quantum number is J. So you got to pay attention if orbital is there or not. Multiplicity and spin get confused with people, okay? So you take the spin, S, and multiply by 2 and add 1, then you get the multiplicity. So let's go back to the last part here. Okay, so this is that table that I showed earlier, and that table gives, like it says, the ground state electron configuration. So these are the term symbols for the ground state electron configuration. So this is the ground state electron configuration, that 2s2, 2p2. Okay. These are all of the excited state electron configurations. If I take the 2p and move an electron up to the 3p, it's still a p2 system, but it's an excited electron configuration, right? Do y'all see the difference between this, a 2p2 right here versus a 2p and a 3p? This one absolutely has to be excited. These all have the same electron configuration as the true ground state. There's only one ground state. It's up here. So this, with the J equals 0 term, this is the single and only ground state. But if we're talking about the configurations, there's 5 of these levels that have the ground state configuration. And that's what was given in this table. But instead of having you just memorize that table, I wanted to teach you the Clebsch-Gordon series, which gives you all of the electron configurations. All of the terms. And not just for the ground state electron configuration, but also for these excited state electron configurations. So we can see all of the, triplet D3 and so on. Here's a triplet D3, and it has the little J values of 3, 2, and 1. Here they are, 3, 2, and 1. And so look how close in energy they are. So these little J values don't give you much change in energy, but that's the spin-orbit coupling. So the electrons are in an orbit as they rotate around the atom, if you want to think of it that way, even though I've tried not to, It's not a planetary system, but the orbital vibrations look like they're rotating. If you think about it, the lobe squeezes out here, and then it squeezes out there, and then it squeezes out here, so it looks like it has a rotational motion to it. And that generates a magnetic field. So the orbital generates a magnetic field if it has angular momentum, like a p orbital or a d orbital or so on, or the electron cloud in a p term or a d term. So that orbital configuration of the electron cloud has angular momentum, which generates a magnetic field. And then the electron, that tiny little 1/2 electron, can be with that magnetic field or against it. And so it can couple. So think about all of the different orbitals you have and all the different ways to put the electrons in it, and you get a lot of little energy level differences. So that's what we're calculating, these tiny little differences due to that little electron out in a d orbital being spin up or spin down. So there is an energetic difference between the little magnets coupling with the magnetic field of their orbitals. So that's the basis of spin-orbit coupling. It looks really complicated in terms of the number of options you have, but the way to get this sort of categorization, the quantum numbers of those, is not difficult, it's just tedious. So hopefully this course is teaching you the difference between something that's hard and versus something that's tedious. It's not hard, but it is tedious. Just like peak picking. It's not hard, but it's tedious. And if you want to do science, I'm sorry, there's a lot of tasks like that. It's not difficult, but it's tedious. Making up serial dilutions and being very careful about that, there's nothing hard about that. But you got to pay attention. You gotta do that. So whether you're peak picking or making serial dilutions, there's a lot in science that you just got to buckle down, put on some music, and just start working the problem. It's not hard, but it is tedious. Now, this is sort of an analysis of where these terms, notice how they, these are the terms that we generated for carbon. Their energy level differences change as we go down the periodic table, but notice they converge over here. And this is what we've learned is Russell-Saunders coupling. There's a little different coupling scheme for the heaviest atoms, okay? And so we're just going to learn this bottom one. So, okay.